rotation around any axis. Last time we found the expression for total angular momentum for rotation with angular frequency omega aligned with coordinate z. This time we will consider the general case of rotation about any axis. We know that the total angular momentum is given by our sum of all the chunks of the solid body alpha, r alpha cross the velocity of this chunk, which is entirely due to rotation and therefore can be written as m alpha r alpha cross, and here we have omega cross r alpha. Because we do not require any longer that z-axis is aligned with angular velocity omega, we write generally that L sub x will be determined by the component omega sub x, component omega sub y, and component omega sub z. The coefficients in front of this, the first one will be given by I sub xx, the second one I sub xy, and the last one will be I sub xz. Likewise, for the Ly component, we'll have I yx omega x plus I yy omega y plus I yz omega z. And the same logic applies for the z component. The coefficients of proportionality, for example Ixx, are simply the sums or integrals of individual mass m alpha corresponding to the chunk alpha, then y alpha squared plus z alpha squared, and Ixy will be given by the minus sum of m alpha x alpha y alpha, and yxz will be given by minus sum of m alpha x alpha z alpha, which again will come just from plugging in the definition of the cross product above. We can write the coefficient I sub ij in a more compact form as a sum of all alpha chunks m sub alpha times, and here we have Kroneker's delta, delta I sub j, times the sum of a different index, let's call it index k, of r alpha k squared minus r alpha I times r alpha j. Obviously, my notation r alpha 1 is x alpha, r alpha 2 is y alpha, and r alpha 3 is z alpha. Kroneker's delta is defined it's 0 whenever the indices are different, and it's 1 whenever they are the same. Thus we write that total angular momentum is given in terms of the angular velocity omega, in terms of construct I, which is given by the coefficients I sub ij. Not to confuse I with a unit matrix, we will give it 2 hats. The object I is known as the tensor of the moment of inertia, and it has components given by I sub ij, I x x, I y y, I z z. It's not hard to see that this tensor will always be symmetric when it's written as a matrix like this. So it will be symmetric across the diagonal. Note that moment of inertia is not just a matrix but a tensor, because the components of the elements of the moment of inertia get transformed each time we choose a different set of unit vectors, x hat, y hat, and z hat.